Okay, today what we are going to do is look at this expression that we talked about earlier for a two-dimensional signal. For most purposes, we'll just call that an image, which is sampled every x meters in x direction, every y meters in y direction, and we get the output f of m. And our goal is to understand how are the frequencies in this continuous signal, this continuous two-dimensional signal, get mapped to this discrete two-dimensional signal. And after that, we want to briefly touch upon the ideas of interpolation, decimation and interpolation in two-dimensional signals. And with that, we will finish our discussion of sampling theory as far as this course is concerned. Okay. So if you guys recall, last time what we had done was we had said that similar to the one-dimensional case, we want to write this expression as first multiplication with a Dirac comb, okay? And after that we want to talk about convert the comb into sequences, convert to 2D sequence. And the reason we did that was because we can first, so if we call the output of this multiplication as fsx of y, and we studied that, what does the Fourier transform of this fsx of y look like in relation to f of xy? So if we understand that, understanding how do the frequencies in f and m relate to fxy become much easier. Okay, so let's look at what does the Fourier transform for 2D discrete sequences look like. And it, as you would expect, just a simple extension of the 1D case. So we'll first define, we'll call it discrete Fourier transform. You have to be careful with the discrete Fourier transform that we study in the case of finite duration sequences, which we will study later, but I don't want to write discrete time because it's not a time signal that we are talking about. Okay, discrete Fourier transform of 2D signals or sequences. And the idea is that if you have a sequence f and m which belongs to L2 Z2, okay, which is simply the collection of all f and m such that they are absolute summable. So if we sum up all the values and take the square, that is less than infinity. Okay. Then the Fourier transform of all the sequences, these two-dimensional sequences which are finite energy, that is simply defined as f of e to the j omega 1, omega 2. As you would expect, there are two variables, so we have to talk about frequencies in two dimensions. Okay, omega 1, omega 2, it's exactly the same meaning as we saw earlier for continuous two-dimensional sinusoids. So I'm not going to show you those pictures again, but what it says is you go from n to minus infinity to infinity, m minus infinity to infinity, f of nm, and you multiply them with these complex exponentials, omega 1n plus omega 2m. Okay. And you should, of course, be aware that it doesn't matter whether I put this summation over n first or m first. They are interchangeable. Not always, but because of the assumption that we are dealing with finite energy sequences. Okay? So sometimes I may write m here, sometimes I may write n here. There is no harm in writing one before the other. And if you want to actually think about how you may want to compute this discrete Fourier transform, for example, I could write the summation over m first, and I could write the summation over n f of n m Okay, and I can write e to the minus j omega 1 n. So I'm just going to break up this exponential and write the other exponential outside the summation because that does not depend upon n, so I can write it outside that summation. Now if I look at this, what is this? This is just the Fourier transform of fn with any fixed value of m. Okay, it's if I fix a value of m, then this is simply I'm summing over all n's and then multiplying by e to the minus j omega 1 n. So this is just the 1D, and now I'll just write dtft. 1D dtft in, let's call it n direction for a fixed m. Okay, and once I write that, then what it says is the 2D discrete Fourier transform is simply you take the 1D Fourier transform in one direction, and then whatever the result you get, you take the 1D Fourier transform in the other direction, because whatever sequence comes up here, you are just taking now, multiplying it with e to the minus j omega 2m and taking and doing the summation, which becomes another Fourier transform, 1D Fourier transform. And this is in two-dimensional processing, this is a common theme that occurs again and again. Okay? Many times what you can do is to do 2D processing, what you can do is do 1D processing in one direction and then use that result and do the 1D processing in the other direction of that result. So that's just a detour, but what we really want to now understand is the relationship. So goal is to understand the relationship between the discrete Fourier transform of the sequence that we obtained from sampling and the continuous Fourier transform of the continuous signal that we started with. So f of j omega 1 omega 2. Okay. Now to do that, we'll first, as I said earlier, we'll first relate the Fourier transforms of these two things. Okay. Just like the 1D case, we will relate the Fourier transform of the sequence to the output or after we multiply our signal with the direct comb. And in the last class, we had already investigated what does the Fourier transform of the direct comb multiplied signal look like. It just consists of multiple copies of your original 2D Fourier transform, and each copy is just scaled in amplitude by 1 over xy. So we already know that if we can set up the relationship between fsxy and the sequence, we'll know the relationship between the sequence and the original signal. So to do that, let's write down. So what does the Fourier transform of fs j omega 1 omega 2 look like? If you remember our fsxy, because of the definition, right, that is simply given by summation of n, summation of m, f of nx my, delta of x minus nx, delta of y minus my. All that this fsxy looks like is these nails sticking out of your plane with the height of each impulse being proportional to f nx and my. Right? But by definition, this f nx my is nothing but f of nm. So previously we had written the Fourier transform of fsxy as a function of the original signal. Now our goal is to write it as a function of the discrete sequence. So for that, we will just write down the Fourier transform of this and use the definition of the Fourier transform, which is simply that we take integrals, the two-dimensional integral of this, and multiply it with the 2D sinusoid. So all I get is minus infinity to infinity, minus infinity to infinity, this summation over n, summation over m, okay, f of nm, delta of x minus nx, delta of y minus my, times, I'm going to write that next term below, e to the minus j omega 1x plus omega 2y dx dy. And now, by simple fact of the sifting property and the integration, I just take this out, nm, and just want to remind, whenever I don't write in summation the indices, the assumption is it goes from minus infinity to infinity, okay? Just trying to save some time. So we can write that as e to the minus j omega 1x, e to the minus j omega 2y, delta of x minus nx, delta of y minus my, dx dy. And now I'll just do the integration over both. Sorry, I should have f of nm here. So that stays here, f of nm, e to the minus j omega 1x, delta of x minus nx, dx, and e to the minus j omega 2y, delta of y minus my dy. Now by the sifting property, this will simply become e to the minus j. This will become e to the minus j omega 1 n capital X. You multiply a function with a with an impulse, you get back the function value at the location of the impulse times that impulse. So this inner thing is simply e to the minus j omega 1 nx times delta of x minus nx. And of course, this thing is not a function of little x, so I can take it outside the integral. And since integration of an impulse is 1, this whole thing reduces to simply e to the minus j omega 1 nx. And similarly, I can do the same for this other integral, which is a function of y. And the net effect is that I get nm f of nm e to the minus j omega 1 n capital X times e to the minus j omega 2 m capital Y. So this is my Fourier transform of the signal that I obtained by multiplying this direct comb with my original signal, j omega 1, omega 2. Okay. And now let's remind ourselves of the formula for the discrete sequence we had, omega 1, omega 2. That is given by nm f of nm e to the minus j little omega 1 n e to the minus j little omega 2 m. So if I compare now these two, if I compare the Fourier transform of this direct comb signal with this discrete sequence, they are exactly the same, with the only difference being that instead of little omega 1 here, in the other case I have omega 1x. Similarly, instead of little omega 2 here, I have little omega y. Okay? Which is exactly analogous to the 1D case we saw, where the only thing that happens is effectively a scaling of your frequency axis. Now, what you are seeing is you have scaling of your frequency axis for both the frequencies. Now you have two frequencies, both of them are being scaled. So if I want to write it explicitly, what I'm seeing is that this Fs j omega 1 omega 2 is nothing but the Fourier transform of e to the j little omega 1 omega 2, with the difference that for little omega 1 I replace that with capital omega 1 capital X, and little omega 2 I replace that with capital omega 2 capital Y. Okay, and I can simply write that as f e to the j omega 1x omega 2y. Okay. So what this is saying is the Fourier transform of this direct comb, if you take this direct comb thing, fsxy, and you convert it into a 2D sequence, f and m, the effect of that is that your frequency axis simply gets scaled. Nothing else changes. Okay? If you, right now we are looking at this way, right? If you have the sequence, you go back to the direct comb, then you simply divide your frequency axis, the x frequency axis by capital X, the y frequency axis by capital Y. Just like in the 1D case, we divide our frequency axis by capital T. On the other hand, if you are going from here to here, you multiply your frequency axis by x in the x direction and y in the y direction. Okay? So this is the relationship. If you are going this way, you have little omega 1 gets replaced by capital omega 1x, little omega 2 gets replaced by capital omega 2y. And similarly, if you are going from this way to this way, capital omega 1 gets replaced by little omega 1 over x, and capital omega 2 gets replaced by little omega 2 over y. Okay? So if you want to write what is the Fourier transform of the discrete sequence, if you know the Fourier transform of this fsxy, then that is simply equal to j omega 1 omega 2. That is equal to fs j omega 1 over x omega 2 over capital Y. So now we know the relationship between when we take this direct comb and we convert it into a sequence, or we take the sequence, convert it into a direct comb type of signal. We also know the relationship from last class, the relationship between fxy and multiplied by fsxy, fsxy. If we have this, we know what is the relationship between the Fourier transform of this and the Fourier transform of my original 2D signal. Okay? So if you remember, what we had derived last time was that the Fourier transform of this impulse sample or comb sample 2D signal is simply you have a scaling of the amplitude 1 over xy, and you get multiple copies of your original Fourier transform given by j omega 1 minus 2 pi over nx and omega 2 minus 2 pi over my. Okay. So if we just now plug in, if you look above, we already know what the Fourier transform of the discrete sequence is in relation to fs. We know what the Fourier transform of fs is in relation to my original signal. So I can simply figure out that the Fourier transform of my sequence, which I obtain by sampling every x meters in x direction, every y meters in y direction, that is simply given by 1 over xy summation of n summation of m f of I actually made a typo here. This is supposed to be omega 1 over 2 pi over nx. So this division, of course, is not supposed to go throughout. So omega 2 minus 2 pi m over y. Okay. And now if I plug in omega 1 equal to little omega 1 over x, then I get little omega 1 minus 2 pi over n whole x, little omega 2 minus 2 pi over m whole y. Okay. So this is the relationship which, if you think back of the relationship between when we sample the 1D signal, it looks very similar to that. In the 1D signal, we get 1 over t. We have one summation, and of course, we have one frequency. So t takes the place of capital X, and of course, we don't have anything called capital Y there because it's one-dimensional. But if you want to now understand what this means, we have these 2 or 3 steps. One is, so if we get f of nm by sampling f of xy as, so our sampling rate is 1 over x and 1 over y, so f of nx my. Then the Fourier transform of f and m is related to the Fourier transform of fxy in the following way. Number one, we get multiple copies of f of j omega 1, omega 2. Okay? So these multiple copies are reflected through these double summation n and m. Now, each of the copy, first of all, has amplitude scaled by 1 over xy. Okay. Further, each copy, so that is reflected through this 1 over xy factor. So we have taken care of what the summation means. We have multiple copies. 1 over xy means we have amplitude scaled by 1 over xy. This whole division by x in the first variable and this whole division by y in the second variable means we have scaling of the frequency axis. Okay, so each copy that we obtain has frequency axis scaled by 1 over x, so scaled by, so we multiply it with x, so scaled by x in omega 1 direction and by y in omega 2 direction. Okay. And the last part is that after that scaling, we shift each copy by multiple of 2 pi. So each copy with the scaled axis, with the scaled frequency axis, is shifted by multiple of 2 pi in omega 1 direction and 2 pi in omega 2 direction. So it's a simple extension of the 1D case that we saw, where again the Fourier transform is simply given by multiple copies. Each copy has amplitude scaled by 1 over t. The axis gets scaled by multiplication with capital T, and then you shift them by periods of multiples of 2 pi. Okay. So let's look at what this may mean pictorially. So let's assume, as an example, that you obtain fx. So you have fxy, you do sampling, you get fnm. Okay. And this fxy has the Fourier transform, again, the pyramid kind of structure that we saw earlier. So let's say that this is my Fourier transform. Okay. And this point is omega n1, this point is omega n2. So what this is saying is, first of all, and if let's say this height, the top part is at height a, okay? So if you want to find out the Fourier transform of f and m, you first of all figure out what the main copy looks like, and you just then shift it around, okay? So the main structure that you need to look at is the following one. You should be looking at then 1 over xy f of j omega 1 over x little omega 2 over y, okay, which is the copy that is centered at 0, 0. Because if you understand what this looks like, then you just now shift it around at 0, 2 pi, 0, 4 pi, 2 pi, 2 pi, and so forth. Right? So what would this copy look like? Of course, the main assumption is that your height is scaled by 1 over xy. Okay? So if this was my pyramid, the height of this thing now becomes 1 over xy. Now this point, now we are in little omega 1, little omega 2 axis. Okay, this point gets multiplied by capital X. And this point here gets multiplied by capital Y. Okay. And now we just take this copy and we put it at every possible shift in X and Y direction. So what are the so effectively in the discrete domain we have now this. In the discrete domain we have a lattice. This is 0, 0, this is 0, 2 pi, 0, 4 pi, minus 2, 0, minus 2 pi, 0, minus 4 pi. And similarly here. And we have all these shifts given by multiples of 2 pi shifts in X direction and Y direction. Okay. And what happens is that each one of these copies, which now I'm not going to attempt to draw the 3D version, each one of these copies now gets shifted to, instead of at 0, 0, at the center points of these lattice locations. So we get one copy which is here, okay? One copy which is here, one copy is here, and similarly all copies here also. And this should all, of course, be regular, whatever is the touching point. I'm not drawing it that carefully. Okay, they should all have the same shape and same distance from each other. Okay, and whether or not these endpoints overlap, that will be a function of how high your sampling rate is. So there will be no overlap here as long as you satisfy the Nyquist criterion. Okay, this will only happen if your sampling rate, if your 2 pi over x is greater than or equal to twice omega n1. Otherwise, you will have overlaps in all these copies, not just this. In all these copies, you will have overlap in around this point. And similarly, you will have overlap here. Whether or not you have overlap here will depend upon whether or not you satisfy this Nyquist criterion. 2 pi over y is greater than or equal to 2 omega n2. Okay. And that goes back to if this criterion is satisfied, right, you can verify that if Nyquist criterion is satisfied, then you can actually verify that this omega n, this should be omega n1, sorry. Omega n1 x has to be less than or equal to pi, just from this condition. If I multiply it here, omega n1 has to be less than or equal to pi, which means if the only time overlap will not happen is if this thing stays below pi. Okay? Which again goes back to the notion that the highest frequency in discrete domain can only be pi. Similarly, this condition, so if Nyquist criterion is satisfied, then omega n2 y will be less than or equal to pi. Okay, which means that this main copy, if Nyquist criterion is satisfied, this main copy will lie within a rectangle, within a square of each side will have dimension 2 pi, right? So this thing will be 2 pi, and this thing is 2 pi, and your whole main copy will lie within this square of 2 pi by 2 pi region. Okay, again very similar to the 1D case. There we were only dealing with you have no overlap. If the Nyquist criterion is satisfied, then the first main copy lies between minus pi and pi. It doesn't go beyond minus pi to pi. Okay, so this is the relationship between the Fourier transform of the signal, the 2D signal that you sample and its sequences. And of course, the same relationship holds if you try to think of sampling. So if you say that you are going to reconstruct a sequence, so if you have f of nm and you reconstruct a sequence to get some f hat of xy. Okay. Then the reverse procedure happens, which is that f hat of xy, assuming you have these ideal 2D low pass filters, this f hat xy simply corresponds to a scaling of the region in the discrete frequencies between minus pi to pi in x direction and minus pi to pi in y direction. Okay. So let's look at that formally though. Recall that the reconstruction formula is given by, we do summation nm of all the sequence and multiply it with this 2D sinc given by x minus nx over x and sinc of y minus ny over y. Now once again, the right way to understand what will be the relationship because of this reconstruction is we do the same trick. We first take the sequence and we convert it into a direct comb, convert to fsxy, where fsxy is simply defined by you take the sequence value and you put an impulse at the location, at the right location with height f and m. So this is the definition of this is exactly as before. Fsxy is defined to be nm f and m delta of x minus nx delta of y minus my. Okay. And so at the output you have fsxy, and then you simply do a 2D filtering with some filter h and m, whose Fourier transform is given by hr. So let's call it hr and m. hr j of omega 1, omega 2, and f hat xy. The ideal reconstruction filter, as we talked about earlier, ideal reconstruction filter is simply hr of j omega 1 omega 2. It's simply a box which is that it is given by this box in x and y direction with height of 1. Okay, it cuts off everything. So it cuts off everything in x direction which is bigger than pi by x. Okay, and in y direction it cuts off everything which is bigger than pi by y. Okay, so that the generalization of the 1D ideal reconstruction filter, which cuts off every frequency above pi by t. So this is minus pi by x, and this is minus pi by y. So hr of j omega 1 omega 2 is simply equal to 1, or if you, so this will be to make sure that we get the same height as before. Actually the height of this thing should be x times y. It will be xy for all omega 1 less than or equal to pi by x, and omega 2 less than or equal to pi by y. Okay, and it's 0 otherwise. So in the presence of reconstruction filter, we can write down that we already know the relationship between the Fourier transform of fsxy and fnm. We just did it previously. We know that the relationship between the two is simply a scaling of the frequency axis. So that is e to the j omega 1x omega 2y. And now we are saying that we are doing a 2D filtering. And filtering simply means multiplication of the Fourier transform. So if you want to write the Fourier transform of f hat of j omega 1 omega 2, that is simply equal to multiplication of the Fourier transform of fs multiplied by the Fourier transform of the reconstruction filter. Now, under the assumption that I'm dealing with this ideal reconstruction filter, all I get is that I'm going to put now this value of fs, so I get e to the j omega 1x omega 2y, okay, as long as omega 1 is less than or equal to pi by x, omega 2 is less than or equal to pi by y, and 0 otherwise. Now, what does that mean? If you look at omega 1 is less than or equal to pi over x, right? This, of course, means that omega 1 capital X is less than or equal to pi, and this means that omega 2 y is less than or equal to pi. So what this means is, let's say I am given a sequence. So I'm given a sequence whose Fourier transform is f e to the j omega 1 omega 2. And again, I have to draw a lattice because it's periodic repetition at all the places. And the Fourier transform, let's say, look like this. Now I'm just changing the figure that I was drawing earlier. Whereas this means the support of the Fourier transform. So there is something rising above it that I'm not showing. Okay. Now, the equation that we have derived, what that says is, you can read it in multiple ways, but the way I will describe is that you basically look at the region of this Fourier transform between the square captured by from minus pi to pi in omega 1 axis and minus pi to pi in omega 2 axis. So you just look at this square region, okay, and you pull that out because that is due to the filtering operation. And after that, since I actually talked about scaling, I should have xy here too. Okay. So you pull that out, and you'll get sort of this thing which lies within minus pi to pi in x-axis, minus pi to pi in y-axis, and then you do a scaling of your frequency axis by dividing by x in this direction. Okay, so now to get frequencies, whatever this was, let's say if this was pi, this will become pi by x. Similarly, if this was also pi in the y direction, this will become pi by y. Any other point in here, any point in here, let's say that this was, assume that this point here was pi by 4 and pi by 6, okay? That point will get transformed to pi by 4x and pi by 6y, okay? Because every frequency in the original minus pi to pi region gets scaled, the x frequencies get scaled by 1 over x, the y frequencies get scaled by 1 over y. So if you had a frequency which was at pi by 4 in the x direction, it becomes pi by 4x. If you had a frequency at pi by 6, it becomes pi by 6y. So let's take the example of a sinusoid f and m. F and m equals to cosine of pi by 3 n plus pi by 6 m. Okay? So this is a 2D sinusoid. A cosine, a 2D sinusoid, which has frequency omega 1, omega 2 equal to pi by 3, pi by 6. Okay? Just one sinusoid. If you look at its Fourier transform will be simply an impulse at pi by 3, pi by 6, and of course its conjugate locations. Okay? But if you, so this is a pure sinusoid in 2 dimensions. If I just now convert it, right, it doesn't matter where this sinusoid came from. If I now convert it into a continuous time 2-dimensional signal, by doing that operation of first converting it into that direct comb and then doing a 2D filter with a height of 1 over xy, with a height of xy, then I get back some sequence and I don't have to think twice about what that sequence will be, as long as I understand what is the relationship between the frequencies in the discrete domain and the continuous domain. Okay? Now, the frequencies will simply be equal to, you will have a cosine of pi by 3, okay, times 1 over x times little x. So the frequency, the new continuous time frequency will simply become pi by 3 capital X, which is little omega 1 over x, okay, plus pi by 6 into 1 over y times y. So the frequency in capital omega 2 will simply become pi by 6 times y, which is omega 2 over capital Y. Okay? So simply a scaling of the frequency axis, your frequency gets scaled to a different location based upon what your values of x and y are. And similarly, since your ordinary signal is nothing but made up of a collection of these sinusoids, each one of these frequencies will just get shifted to the right location. Okay? So, and the reason we don't have a scaling of the amplitude here is because of the impulsive nature of the Fourier transform. Let's say xn is cosine of pi by 3n, and I pass it through a discrete to continuous block with some time period t. I'm not going to get t times cosine of pi by 3 over t times t. Okay, the answer will still be cosine of pi by 3 t times little t. The reason for that So this is my, let's say, x of e to the j omega. And I now want to get, because of the discrete to continuous conversion, I want to get x of j omega, which is given by x of e to the j. So let's say that there is time period t associated with it. So that is capital omega t. So let's look at what does this mean in terms of this relationship, right? One way to define an impulse will be that I take delta of x equal to limit t goes to infinity of some function ft of t, and I can take this ft of t as simply this rectangle which goes from minus t by 2 to t by 2, and its height is 1 over t. I have it other way around. Yeah. So its height is t, and it goes from 1 over 2t to minus 1 over 2t. So if you look at the area of under the curve, area of ft of t, right? That is simply t times 1 over t, that is equal to 1. So that's the definition of a rectangular, that's the definition of an impulse, the mathematical definition of an impulse, right? The key characteristic is that area under the curve has to be equal to 1. So if you want to now think about how do you translate delta of omega, so we don't have to, we can without loss of generality take omega not equal to 0, doesn't matter. And if I'm saying if delta of omega, I want to translate into what does scaling of the frequency axis mean, I should really think about in terms of this definition of my impulse. Okay, so I should really think of it as limit t goes to infinity ft t or ft omega. Okay. So now if you want to say I want to scale the axis by the amount of, I want to divide my axis by t, right? So what does this ft, so what does ft capital omega t look like? Now I have a scaling of the axis, right? I shouldn't use the same t. Let's use capital X here. Okay. So I get 1 over 2 tx minus 1 over 2 tx. Okay. And the height is still t. Right? This thing is only scaling my x-axis. Right? It's not going to scale the amplitude. So what is the area of this thing now? What is the area of this thing? It's 1 over x, right? So if I want to make it an area of 1, what should I do? I should multiply this amplitude with capital X. Okay? If I multiply it with capital X, then my area of x times ft omega x is equal to 1. Okay? That's why the front factor does not appear if you take delta of omega minus omega naught and you say just scale the frequency axis and not change anything else, then the answer is actually delta of omega minus omega naught times 1 over t. And if you have a scaling factor of t here, then that t gets cancelled with this 1 over t. Okay, so if you have this scaling factor of t, then that t comes here and it cancels, and then you get your pure impulse. Okay, so the upshot is that when you're doing the scaling of the frequency axis, in the case of impulse, we have to be careful that you don't put the multiplication factor in front. Okay, that's why in this example, I'm not putting 1 over x, y in front. I'm not putting x times y in front. Because if I were to go through this expression in the frequency axis, that xy will be subsumed in defining my impulse. So these cosines, or when your Fourier transforms have these impulses, you have to be careful about the definition of what the scaling the frequency axis mean. Okay. If you scale the frequency axis, you have to also scale the amplitude. And that's why the multiplication factor in front doesn't show up. The next topic we want to discuss in this discussion of 2D signals and images is that of downsampling and upsampling, which is again a very common thing that we do with images. For example, we take images and they look very large. They are maybe like 5 megapixels by 5 megapixels or something. We want to reduce their size. That is effectively a downsampling operation. Or we have a small image and sometimes we want to make it big. That's an upsampling operation. Right? So just like in the 1D case, in 2D, concepts of downsampling or decimation and upsampling expansion and interpolation. So expansion is different than interpolation. I'm just saying that upsampling consists of this expansion operation and a low-pass filter. So these concepts also apply with some exceptions, because the extensions are not as straightforward as in the 1D case. You have more than one way of, for example, doing downsampling. Okay, I'll just give you an example, although I won't talk about those cases. I'll just talk about the canonical decimation that we do in 2D signals. So let's say you have a sequence, and now I'm not drawing the Fourier transform. Now I am drawing the, so this is NM space. Okay, this is 0, 0, 0, 1, 1, 0, 1, 1. Okay, so this is 0, 0, and I have all the connections. And what I want to do is I want to downsample by a factor of 4. So downsample by 4, which means that for every 4 samples, I want to keep 1 sample and throw away the other 3. Okay, so in the 1D case, it was very easy. In the 1D case, we had these samples 0, 1, 2, 3, 4, 5. And what we said was, well, you start at 0, keep 0, throw 1, 2, 3, keep 4, throw 4, 5, 6, 7, and so forth. right? There is no other, if you want to keep 0, there is no other option available to us. Now let's think about the 2D case. In 2D, actually that is not true. If I say I always want to keep 0, 0, which is the convention that we follow, what are the 4 samples that I could pick? For example, I could say this, 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 and this, they are 4 samples. And I'm going to draw this sort of little parallelogram. I can keep this 0, 0, and I can throw this, and throw this. That is one option, right? Or I could say that I'm going to actually work with the more conventional picture that you may think, which is this one. Okay, I actually keep 0, 0, and I throw this, this, and these 3. So in 2D, when we are talking, and similarly in higher dimensions, when we are talking about downsampling, the question of how to do downsampling, that becomes a little more involved than simply keep one, throw the rest, and then keep one. Okay, because you have 2 directions to follow. How you trace that route determines which samples you keep and which samples you throw away. Okay, so we won't go into those details. What we will do is a simpler version of 1D decimation, which is exactly that you follow with this notation. Okay, you keep you treat every line of this as a separate sort of 1D signal. You throw away every sort of D1 samples there, and then you go in the other direction and you throw away every D2 samples in that direction. So the sampling operation that we will follow is a restricted version of that, which we'll write as D1, D2. Okay. In general, downsampling, I'm just trying to say it so that people who are interested may read it somewhere. But in general, downsampling in higher dimensions is actually represented through a matrix. Okay. But we will just use these 2 numbers, which effectively means that our new downsampled version FDNM equals f of n d1 f of m d2, okay, which can be implemented by first downsampling by d1 in n direction, and then downsampling by d2 in the m direction. So what this means is if we had a sequence, let's say 1, 2, 3, 4, and let's say we are interested in doing 2, 2 downsampling or decimation. Okay. So first you go in x direction for every sequence and you throw away every second sample. So you go here, throw this away, okay? And you are left with now these samples. So you are now finished downsampling in the n direction, in the x direction, whichever variable you want to use. And after that, whatever is remaining, you now downsample in the other direction. So now you have, for every line, you go and throw away one sample, keep the other. So you now throw away this, and you now throw away this. Okay. And similarly, you keep on doing, and what you will have is sort of this box that I had drawn earlier. You are sort of doing this canonical, if you want to call it, or elementary downsampling. That is not the only way, but that's the easiest way, and that's the way that we'll stick with in our discussion. Now, what does downsampling, of course, do in the case of images is, if you think of these values now, let's say you are given an image, right? If you are given an image which has all these pixels, and you think of these samples as your pixels, then downsampling effectively, this 2 downsampling, it's going to reduce your number of pixel count by 5-fold. So if you started with, let's say, 4 megapixels, after this downsampling operation, you get back 1 megapixel. Right? You have 4-fold reduction.